This is a project that I think Mike's been working on for close to 15 or 20 years. And I think even Nick did a little bit of help about a decade ago. And I started helping myself as a Hollings student in 2017. So this has been the culmination of a lot of people's work. And we're finally getting to a point where we're ready to share a little bit more about this and hopefully get a paper out here sometime in the next year or so too. So for those that haven't heard the term before, significant wind-driven hail, we define it as a severe thunderstorm that's simultaneously producing significant wind and golf ball or larger sized hail. And when they do occur, they produce extensive damage both to property and crops. And in extreme cases, the damage can exceed up to $1 billion. And we'll actually go through one of those cases later on in this presentation. These events occur across the United States with a tendency to be focused more in the southern and central Great Plains. But despite a fairly extensive damage-producing storm, there's very little existing wind-driven hail research. There were a couple of case studies in the mid-1990s. The Klimovsky paper is still, again, mostly a satellite-based analysis of a wind-driven hail event, but even recent work is largely focused on that post-event satellite analysis versus actually looking at some of the factors that are producing wind-driven hail in the first place. So that's part of our motivation, and then the second part of our motivation is the recent shift to IBW tags and WIA alerts for severe thunderstorm warnings, where you can now select specific call to action statements for wind-driven hail, both possible and observed. And while we have those call to action statements, we don't really have any techniques or tools at this point to help forecasters predict that. So we may not be able to necessarily protect crops or property, but if we can start to get a better sense of what's causing these events, maybe we can help produce or prevent some unnecessary damage in cases. And so that's the main goal of this, and we'll focus on this top part of this objective screen, is to develop a database of significant wind-driven hail events, and that's what we're going to be talking about today, where we identify those events and then look at the near storm environment and radar characteristics of these wind-driven hail events, and then look to see if they share common characteristics. So the longer term goals are finding ways to identify and differentiate between these storms ahead of time, but also look into some of the modeling and stuff. So if we can run some of these cases through an idealized model like CM1, can we kind of see what's happening within the supercell itself that's causing this in the first place? And so to develop this database, we're looking at hail and wind reports from the SPC's database from 2010 to 2019. It's supposed to be a proxy for the storm data set that's available online that WFOs produce every month. And then we take that data and we query in ArcGIS for instances of the golf ball or larger sized hail and 65 knot winds. And they must occur within 10 miles and 15 minutes of each other. And this isn't a perfect searching mechanism, but what we're left with is close to 50 to 75 potential events per year. So in total, from the 2010s, we were looking at roughly 700 potential cases. And then we would manually investigate each one of these using a variety of different data sources, radar data and GR2 analyst. We're looking at the storm data narratives. We're looking at LSRs and LSR descriptions, also traditional and social media reports. And sometimes it was just as simple as Googling the town name and then hailstorm and then the year and seeing if you could get any YouTube videos or local news stories out of that too. So we were looking at a lot of different things for roughly 700 cases over the course of 2010 to 2019. So it was pretty thorough. And once we got this database set up, then we requested SPC mesoanalysis data. They provide it in GEMPACK format, and then we parse it for the nearest grid point through Google Colab Python notebook. And so anyone that's used storm data to do research is probably already thinking about raising their hand or typing a question or comment in chat. So it's worth a couple of slides talking about some of the limitations here. And so these are mostly well documented already, where there's poor temporal and spatial density. If you read the paper from Scott Blair in 2017, they were looking at high resolution hail data sets and comparing it to what was in storm data in our LSRs. And a lot of the times they were finding that there was hail in a lot of these events that was significantly larger than the biggest report we get in an LSR. Additionally, most of the data and storm data is point data versus swaths, and we know that hail and wind are not contained to a single point. They occur over a much larger area than that, but in storm data, for the most part, you're looking at points. There's also just difficulties in gathering accurate measurements, especially for wind, if you're relying on spotters or other public non-instrument sources that have to estimate the gusts. That always leads to a little bit of uncertainty as well. And then there's also just differences in how WFOs go through during severe weather events, how they LSR events as they go forward, especially in high impact events where gathering that fourth or fifth LSR and a warning may not be as important as some of the other things going on during a high impact event. There's also some subjectivity in determining wind-driven hail cases on their own, and without explicit mentions from the LSRs or storm database or having that video or photographic evidence, there's always going to be a little bit of educated guesswork in what we're doing as well. And again, there's also, from what we've noticed, there are a few instances where there was implied significant wind-driven hail through LSRs where, for example, a 75-knot wind report would also mention 2-inch hail, or a baseball-sized hail report would mention 70-mile-per-hour winds. And you just wouldn't have that second corresponding LSR where our query wouldn't pick up on it because there wasn't that second LSRs with it. So there's also things like that. There are also a couple of timing and location errors we've seen where the timing of a hail or wind report clearly doesn't match up with radar. There was one event in Missouri where I don't know if it was a GR2 issue or an IEM issue, but every single LSR during an event was shifted an hour wrong from what I believe was a time zone issue. So there were a lot of different difficulties we'd faced relying on storm data, but we feel pretty confident about the cases we have in here. And the bottom line is we're probably undersampling the total number of events, and that's okay. We really wanted to make sure we didn't dilute our database with false positives. So we're really only including cases that we're confident in. So this is going to be the first time where we call for your help. And if you know of cases in your CWA, especially that have occurred in the last 5 or so years, we'd love to know about it and send it our way. Now getting into the actual data, this is just a really simple scatter plot of wind-driven hail events, and they're categorized by years, the different colors on the map. So again, you can see that clustering across the central Great Plains. I think Goodland had the most cases, followed by a couple of the other offices in Kansas and Nebraska. And you can tell, again, it's really focused over the plains with only a handful of cases east of the Mississippi River. One of the cases in Indiana still ended up being fairly extreme, where at least the largest LSR attached to it was close to softball-sized hail. And there were some 60 to 70 knot winds associated with that one as well. So again, that focuses over the central plains, but anywhere from Montana all the way to the East Coast has seen a couple of events. And this makes sense if you look at the distributions of significant hail and significant wind across the US. There's that tendency for it to be focused again over the Great Plains, especially with that significant hail here. So again, that kind of makes sense, and we weren't really surprised by that finding. Now looking at hail and wind distributions, I know the significant hail by SPC is defined as 2-inch hail. We still use 1.75 inches in ours. And again, that's mostly based on the damage it causes. If you think of putting your house right next to a driving range and having a bunch of adults throw a couple 6-irons towards your siding, you probably wouldn't like that. And that's, golf ball sized hail. So we use golf ball sized hail and 65 knot winds just because of the damage. And you can see there's a lot of binning towards those common objects where golf ball sized hail is much more popular than say the egg sized hail, which is a 2-inch diameter. And then there's really nothing in that 2.25 inch bin. And then once you get back towards the tennis ball and the baseball size hail, you see a lot more clustering again there. So you see a lot of clustering towards those common object bins, and then you have this huge gap between 3 and 4-inch hail. And then you've got a few of those extreme cases where you're looking at softball size hail and greater than 70 knot winds. Looking at just the general timing of these events, it's not surprising that these are generally occurring in the mid to late afternoon and evening hours with a peak between 21Z and 3Z. And most of these are during the warm season, roughly between May and August, with a handful of cases and some of those shoulder seasons. So again, if you think of the timing of when you're getting severe weather in the Central Plains, it's generally that May to August timeframe. So that's not particularly surprising to see. For those that are curious, 99% of these events included some sort of warning. Most of them were severes. There were a handful of tornado warnings, roughly 25% were tornado warned, and 5% of those were tornado warnings with confirmed tornadoes at some point in the storm's life cycle. Generally, from what we found, tornadoes and wind-driven hail weren't occurring simultaneously in a lot of these events, but again, with some of that reliance on LSRs, it's hard to say for sure. We are planning a more in-depth look at the wind and hail tags versus LSR magnitudes for the annual NWA meeting. So if you're curious about that, come and see us again this fall. Now getting into some of these environmental parameters. Again, this is based on SPC's gridded mesoanalysis. And we're just pulling the nearest grid point at the hour preceding the report time. None of this is particularly surprising, where mixed layer CAPE is generally in that modest to moderate range of about 1,000 to 2,500 joules per kilogram. You get a little bit more most in stable CAPE. Some of these events are occurring in elevated environments, so it's not surprising that MU CAPE's a little bit stronger than their mixed layer CAPE. But most of these cases had a pretty good DCAPE, anywhere from 750 to about 1,500 joules per kilogram of DCAPE. And I hinted at this already, but not all of these events are surface-based. You can tell a lot of these events don't have are particularly strong 0 to 3 kilometer mixed layer CAPE. And if you look at mixed layer SIN, there's quite a few of these cases where you're looking at a mixed layer SIN less than 50, negative 50 joules per kilogram. So if you look at this 2D view of it, where you have mixed layer CAPE on your x-axis and mixed layer SIN on your y-axis, you can tell there's quite a variety of different environments where you have some really unstable environments, but still a little bit of mixed layer SIN. So it's not entirely a surface-based environment, and it's not necessarily dependent on getting that surface-based convection, but for the most part, a lot of these events are still surface-based. Looking at shear, again, this isn't particularly surprising, where a lot of these events are going to be supercells, and so you have this pretty good deep layer shear with a median 0 to 6 kilometer shear of roughly 45 knots. Your 0 to 1 and 0 to 3 kilometer shears take over a little bit more of a wide range of parameter space here, where you have a few of these extreme events with really strong 0 to 1 kilometer shear, and some of these are likely those tornadic ones. But you're not necessarily dependent on having that strong low-level shear. You do have pretty good storm relative felicity in most of these events, especially in that 0 to 3 kilometer layer. But again, this is all generally favorable for a supercell environment. Looking at lapse rates, again, because not all of these events are surface-based, you have a pretty wide range of these lower level lapse rates with some very clear low-level stability examples here, but also some very well mixed low-level lapse rates. But there was pretty tight clustering of that mid-level, which is a 500 to 700 millibar lapse rate, really closely clustered on that 6.5 to roughly 7.5 degrees Celsius per kilometer. So that's a good sign that you've got pretty steep lapse rates or loft, which would again favor significant hail as a potential with any supercells you get. Breaking this down in between the different eventual storm modes here. So there's a lot more supercells than these marginal or non-supercell events. There's not a huge distribution or change in the actual CAPE regime here, although these are relatively small sample sizes for the marginal non-supercell cases. But you do see that tendency for the supercells to have the stronger deep layer shear, with the marginal non-supercells exhibiting a less favorable environment. And you can kind of see the same type of thing in the supercell composite and effective significant tornado parameters, where the supercell environments tended to be more favorable for supercells, with a gradual decrease as you get into the marginal non-supercell events. Again, these events don't really have a preferred regime of temperature or dew points. You can see there's quite a bit of range in here, and some of these cooler events are during some of those shoulder season timeframes of March or April or September into October. But there isn't really any preferred regime here for any sort of temperature dew point trends. There's a pretty wide range in dew point depressions and even a pretty good range in near precipitable water. So there's, again, not a really preferred environment here, just one that's favorable of supercells. And we included this in an AMS poster roughly 6 years ago, but we updated it again here. So on the left is our subset of significant wind-driven hail events, and then on the right, this is from the Thompson et al. 2003 paper, where they were looking at RUC proximity soundings for a variety of different types of events. And you can see there's significant tornado cases have this really tight cluster of LCLs around roughly 1,000 meters, with their weak tornado and non-tornadic significant severe environments showing higher based LCLs. And we kind of have that same distribution in our events as well, with maybe a little bit more spread. But some of our events are well mixed, some of them are stable environments, so it's not particularly surprising to see that we don't really match this significant tornado regime, but we're still looking at an environment that's pretty favorable for supercells, whether they're surface-based or elevated. Looking at a couple things with radar here, the left is the freezing level versus 50 dBz height, and then the right is freezing level versus 65 dBz height. That 50 dBz height was commonly used from that paper from Rod Donovan a couple of years ago, where the 50 dBz height can be a pretty good proxy for identifying just severe hail and not necessarily significant hail. But even in our case, we do have a little bit of a linear regression there. It's, the R-squared value is not particularly high, but the one thing that's really obvious here is that there's almost no cases where the 50 dBz height was less than 30,000 feet above the radar level. And there were even some extreme cases up in here where the 50 dBz height was, 50 to 55,000 feet above the radar. So these are obviously very impressive storms aloft on radar. And again, similar distributions here with the 65 dBz height. Generally, you're focused on that 20,000 to 40,000 feet above the radar level, with a handful of cases that had less than that. Looking at rotational velocity and storm top divergence, again, these aren't particularly surprising. These are really strong rotating supercells. The supercell cases had a median VROD of roughly 45 knots. And storm top divergence of about 150 knots. So this actually surprisingly correlates with there's a giant hail paper written by Scott Blair in 2011. These values are actually pretty similar to what they found for giant hail producing storms. So these are very clearly some really strong persistent rotating updrafts. And if you look at the distribution of VROD versus storm top divergence, again, there's maybe a little bit of linearity in there, but there's clearly this range where you're getting 100 knots at least of storm top divergence, and anything above roughly 35 to 40 knots of rotational velocity. So again, given what you're seeing on radar, these are obviously pretty strong supercells, and we're trying to figure out better ways to identify them on radar than just some of these traditional parameters. But for some general notes, almost all of these events were either discrete or semi-discrete supercells. They obviously exhibit a wide range of storm motions here. Anything from about 15 knots to 45 knots was fairly common. But we did start to notice three common modes here. And the first is this high precipitation supercell with extreme reflectivity, so 60 to 70 dBz in your RFD. And actually, if you read that Brian Klimowski paper, it was just a picture of the month thing. Their radar images are a lot less high quality compared to what we get now with the super res, but you can kind of see that implied really high reflectivity in the RFD of that storm as well. So this was one of the more common modes. We also had what we're calling these Selbo echoes, where you have this really sharp gradient of reflectivity kind of right along the leading edge. Sometimes you'll have these cases where you have this really strong downshear hydrometeor lofting. But these Selbo echoes were also really common. And then we also had these kind of elongated or hybrid supercells where, as we'll go through this case study here in just a second, you'll see that this was a really strong rotating storm, but it's not necessarily a look you'd see on radar very common. So it's got supercell characteristics, but it's not necessarily something that's as common. So we just kind of have this elongated or hybrid name for it. So we'll stop for a quick pause here, and then I'm going to turn it over to Mike. But if we have any couple quick questions about the environment, we can take those now.
I'm not seeing anything, Zach. Great job. We had a comment in the chat from Brian. You might want to comment on that. If you can see it.
Yeah, I got to download it first, but we'll get to it at the end. I suppose that'll be easier to do that than making me wait for this to download. So if Mike, you want to take over and you're ready, let's do it.
All right. Well, thanks, Zach. Zach did a really nice summary there of a lot of the background material here. And thanks for reminding me, Zach. Yeah, I've been working on this sort of a project for 15 years. So I appreciate you showing that things haven't quite gotten done yet. So we're trying to make a final push, as Zach said, to get this published and then kind of move on to what we're calling phase 2. So we wanted to conclude here with just looking at a case study from one of these events. And we're going to use an event that, gosh, I can't believe it's been almost 10 years ago, from the 3rd of June of 2014. And this was an event that impacted primarily eastern Nebraska, but it did impact portions of far northeast Kansas as well as southern Iowa as well. This was not a surprise event by any stretch. As you can see, the SBC categorical risk was a high risk on this day, but they were expecting kind of a combination of some tornadoes, some high-end wind, but what we ended up getting was a lot of wind-driven hail. So as you can see here, as Zach mentioned earlier, some of these can be extremely destructive. This was a $1 billion event, and we'll show some of the pictures right now. So you can see the damage that these cause. Obviously, it's not just a bit of damage. It's shredding siding, it's shredding crops. I mean, cars are being demolished. So these are a couple pictures in and around the Blair, Yuling area. The National Weather Service office in Omaha, I'm not sure if anybody's on from the office, but they did a really high intensity storm survey with this, which is really cool. So keep in mind, this is the 3rd of June. And as you can see here, pretty much all of the leaves are stripped from trees as well as shrubs. And it even killed some of the tall grass, which is pretty extraordinary from this event. And I had to show this in Blair, Nebraska. There's a kind of an a zone of automakers. There's the Woodhouse Dodge that's there. There's I think Sid. I'm trying to think of the name here. Sid Dillon Chevy. And yeah, this is beyond the hail sale sort of idea. This is cars totaled. So if there are any car aficionados there, the car on the right is a Dodge Challenger. My brother-in-law is a huge car guy, and that picture literally brought tears to his eyes to see a car that these were essentially totaled. So this, just alone with the car damage in this case, were millions of dollars worth of car damage, and that was just in the Blair, Nebraska area. Okay, so here's the example case that we're going to look at in the main cell. And again, there were several instances in this event. We're going to focus on that little area that you see there highlighted on the map. So this is the base reflectivity loop from starting at 18Z. And we're going to focus on that cell that moves across, you can see across eastern Nebraska during that time frame. The first thing I wanted to highlight is, as Zach mentioned, this is the 20Z analysis here. And you can see where the cell is at about that time. And the synoptic scale warm front was actually quite further south. It was across southern Nebraska. So this storm rode, as we often see, right on that instability gradient, kind of on the north side. This is the ML Cape and Sin. So where that storm rode was, again, right on the gradient area. So this was either a elevated or just a quasi-elevated storm. This was not a pure surface-based storm, again, well north of the warm front. And again, this is a fairly common mode that we see with a number of these events. And if I just show you where this storm happened to be in our scatter plot there that Zach showed earlier, this is just the 0 to 6 bulk shear and the most unstable cape. As we've seen in some recent research, especially from Nixon and Kumjian, you don't always need monstrous cape to get significant hail. In this case, we had some extremely large hail with only about 1,000 joules of MU cape, but we had extremely high amounts of deep layer shear. I mean, one of the higher magnitudes in our study here, almost 70 knots of deep layer shear. So not a surprise that this was in the supercell realm. And again, not monstrous amounts of cape, but obviously sufficient to get very large hail coming out of that. I just wanted to show this. Always good to look at a sounding in a case like this. This is the 18Z observed, not OOBS sounding. This is an observed sounding from North Platte. Probably a fair proximity sounding to where the storms were. As you can see here, you can see why this was a high risk day. If you look at the hodograph structure as well as the instability, thermodynamic structure, very impressive. So you can see why this was a high risk day. The deep layer shear and the low level shear was impressive. So again, obviously tornadoes were in play, especially if these could become fully surface based. But again, where this storm tracked was again in at least a quasi elevated sense. So tornadoes probably were not going to be favorable at the location where that storm was tracking. But again, a very high end environment nonetheless for this event. So we're going to highlight just two areas on radar. One of the first area we're going to show is near Ewing, Nebraska. Again, this is all in eastern Nebraska. And for the sake of time, I'm just going to show a couple over one elevation scan, just a couple angles. Again, if you're interested in looking at events like this, and Zach showed the map earlier, we'd be happy to share events in your CWA if you're interested in looking at it. Obviously, if you can keep it internal, that'd be great. But again, we're happy to share the database as well as the event time frame and such that you can pull these up on GR yourself. So this is the Omaha radar. This is the low level, the lowest level scan, 0.5 degree at 2040 UTC. And again, this is at about 1,800 feet above radar level. And the storm was moving again to the southeast at about 40 knots. So pretty decent storm motion. Again, the radar is just on to the south side of the storms here. And a couple things stand out, as Zach mentioned. This is one of those elongated hybrid structures. So a very long, elongated area of really impressive low-level reflectivity, your horizontal reflectivity greater than 75 dBz. Now, occasionally that can result in a lot of small hail. You'll see as we tilt up that was probably not the case, and it was not the case here. Obviously in ZDR, you can see with the values near zero or less than zero, there was obviously hail in there. And with your CC reduction, again, I kind of highlighted just the reflectivity core. Obviously, you know, there's some mixed phase going on there, different sizes and shapes of hydrometeors. And you can see there, right near that interface where that reflectivity gradient is, there is an interface where the winds are really cranked up. And again, this is the low-level reflectivity. There was likely some larger hail falling out ahead near the Ewing area right now. That would be much larger hail. Again, some of the smaller hail was probably back in that further back core. Your inbounds there, again, the radar south of us, not a perfect sample angle, but we're getting a Vmax inbounds of 75 knots. So pretty impressive velocity structure with this. As we tilt our way up, I just, again, selected the 5 degree scan or 5.1. We're now at about 14,000 feet above radar level. Again, a very impressive weak echo region, wide, persistent updraft, a very broad and intense mesocyclone. So there's your necessary one of your necessary ingredients there for getting a hail growth zone where you're getting long residence time, you're growing sufficient hail. Very nice ZDR column embedded in that as well. So again, you can see the reflectivity of, you know, this is near above the freezing level. Again, still 75 dBz or greater. And then finally, as we tilt up to 12.5 degrees, now at about 35,000 feet above radar level, again, you can see a bounded weak echo region there, and off to the northeast, still 75 dBz. So again, this was not just a splash event. This had some very large hail being, again, falling out right in that wind core that we saw. If you were to translate that back to that original 0.5, some larger hail was falling right into that very intense inbounds towards the radar. Again, we're starting to get in the area where you see the storm top divergence there is increasing. Again, we're not necessarily at storm top here. So again, very impressive reflectivity and velocity structure. Three-body scatter spike, pretty evident here as well. So again, that's the first kind of snippet. The second one will move. Let me go back. Again, we're going to translate right over to the Blair, Nebraska area. And again, all these dots here were areas where the Omaha office did investigate these storms. Again, kind of an odd structure on reflectivity. So you look at this, it almost has this curly Q structure, but you can imagine here in your reflectivity where you're getting kind of almost in essence, a little bit of a rear inflow jet pushing in. Again, very high reflectivity there. You can see the ZDR at the surface below zero. So you're getting hail mixed in there. Again, at this point now, I don't have the radar plotted, but the radar is, you can actually see it there, which is why I don't have it plotted. Again, your winds are going to be blowing, in this case, from the northwest, so you're going to get a poor viewing angle there. So you're not going to resolve your velocity, your radial velocity very well. So again, keep that in mind when you're looking at these sort of cases. But again, you know, we had reports at this point that this storm was producing obviously very large wind-driven hail. As we tilt up again, this is the 5-degree angle. Now we're at about 10,000 feet. Again, a broad mesocyclone, but again, a really well-developed weak ecoregion updraft. Again, very prolific hail growth. Your ZDR column there extending well above the freezing level. So you are getting efficient hail growth in there. And then again, a similar look at, in this case, 12.5 degrees, 25,000 feet. Again, still seeing that really impressive horizontal reflectivity core, 75 dBz. So again, very impressive structure. Again, this is in terms of structure, these are kind of the no-brainer events. But again, what are you thinking? Is it giant hail? Is it wind-driven hail? That's really the answer is a little tougher to come by. But in this case, again, by this point, we had lots of reports of wind-driven hail, significant damage, that sort of thing. So again, that's just a quick couple look for the sake of time. I won't belabor that any longer. But obviously, this event had high societal impact. Again, this was extremely destructive in that whole swath that I showed. Again, this significant wind-driven hail event exhibited the environmental parameter space was in that upper echelon of the Cape Shear, especially the shear parameter space. This was a long-lived, again, kind of a quasi-elevated supercell. Again, I would categorize this as an HP environment. Again, there were a few tornadoes, as noted in that case, not necessarily with this storm, but in that environment. The dual pole analysis was clearly helpful in discerning some of the storm scale details to help identify some of those key features for wind-driven hail. And I'll give kudos to the Omaha office. They did a fantastic job. Again, this was pre-WIA, of course. This is 2014. And again, they had 80-mile-an-hour gusts and baseball-sized hail, which was what was being reported. So not a surprise that you're getting such destruction. Again, in today's world, this would have been a WIA, but in those days, of course, it was not. So as Zach mentioned earlier, there's some new DSS opportunities here. One of the things with Daryl Herzman's help at IEM, we did start to look at the call to actions that you can now put into the warnings that enhance that wind-driven hail verbiage. And we've seen 75 or so of these now included in SVSs. 16 of those have gone out in severes. We're still looking at matching these up and this sort of thing. We actually saw a number of these actually in TOR warnings, which is a bit interesting that the wind-driven hail was in a TOR warning. So again, we're going to look more into this. We just started to look at that in the last couple of weeks with Daryl's help. So again, as Zach mentioned, come see Zach at the NWA and we'll have more details on that. But just as a reminder, right now, if you're in the considerable realm, it's 70 in golf balls. But to get to the WIA part, you have to be 80 in baseballs. So a recent event that we had about a year ago, and again, I'm not sure if anybody is from Hastings is on. Again, a little bit of the cell bow echo kind of structure in this one. This was one where they had 2-inch hail in the warning and 70-mile-per-hour wind gusts. So again, this would have been a considerable tag, not the destructive tag, but notice that they did include the large hail driven by severe winds. Take shelter now. So again, this would not have WIA'd, and we'll get to that in the next slide here. So if Hastings is on, perhaps they can talk about what sort of damage that resulted from this storm. But again, this is the kind of use that we're hoping for or we're looking for when we see these sort of events develop on radar. So the question here, I guess one of my thoughts here is to WIA or not to WIA. As noted there, you saw what the thresholds are to get a WIA in there. There was some early discussions when we talked about the severe WIA to consider significant wind-driven hail. I had proposed actually 2-inch hail and 70-mile-per-hour winds would give you, and not catastrophic, this should be destructive. That's my error there. That would be the destructive or the WIA tag. Ultimately, that was rejected just to keep the criteria simple, and I understand that. But keeping in mind, these are impact-based warnings. If you're seeing an event like this occur, we know that these often have, again, these are, in my mind and a lot of Zach and I's research, these are destructive. So, you know, on those, if you notice one of these events or you're feeling strongly that you're seeing some of the radar characteristics, those preferred archetypes, you know, getting a history of wind-driven hail, you know, adjusting this, nudging the wind up to whatever you need to get a WIA out. Again, thinking of the impact-based warning idea, I wouldn't hesitate to do so because that's often going to help get the word out, right? Your cell phones are going to buzz. As we know, that's the intent of these. So kind of, for lack of a better term, fudging that, in my opinion, maybe a little controversial, but I would not hesitate to get the WIA out. So we can talk about that at the end if there's suggestions. And as Zach mentioned, future work here, we'll go through this quickly. Again, we're trying to get the latest data in here. So again, we have 10 years now. We're trying to get another 3 years. As Zach mentioned, if you have cases from your office, email us. The other thing is in your LSR entries, I know in real time it's hard to do this, to say, you know, golf ball sized hail and then have a separate LSR that has wind of, you know, 75 miles an hour or whatever. But boy, that makes our life easier and it helps the database. If you can do that, that would be great. So yeah, here's a snippet of another wind-driven hail event that we've seen, just to kind of give you some visual on what you'd expect to see. If you're looking for other examples, we have more. You've probably seen some of these in your forecast area as well. As Zach mentioned, we're also going to look at the hail wind tags from these to a little more comparison there. And then again, we're going to expand our radar analysis, you know, to fully integrate. If there's anything else that we might be missing, again, we'll talk about maybe some new proxies here in a second. So again, for the sake of time, we'll move on. Again, future work. So one of the things that may come up here is, are we looking at the right environmental parameters? You know, right in quotations there. At our recent conference here, Matt Kumjian and Cameron Nixon talked about some alternatives that are now out there or that are soon to be out there for at least hail prediction. So things like entrainment cape or E-cape, as well as something like the level of free convection to your equilibrium depth, may be a better proxy for your actual hail potential, large hail potential, more so than some of the traditional methods. But obviously we were bound by what was available at the time. So again, we're hoping to maybe start to look at some of these new proxies or new parameters that may prove to bear some good fruit. And then the same thing with radar proxies, same sort of idea. You know, Matt Kumjian talks a lot about this updraft width and area. You know, the weak echo region of the BWER width or size. Maybe with GR version 3, there's some ways we can start to look at these, the ZDR column area, the KDP column area. There's some really exciting new parameters that we can start to look at here, I think, which will help with hail prediction. Obviously, that would focus or fold into the wind-driven hail prediction as well. And then finally, I am not a CM1 expert, but if those of you that are out there are, I'd be willing to I know Zach's done some work, so we are going to try to simulate this, and Matt Kumjian volunteered his hail trajectory model that we can start to better understand how the exact dynamic processes work. These are not these are not just thermodynamic downdrafts. These have dynamic pressure gradient forces that are there. So trying to understand how these differentiate is really important. Again, that's phase 2. As noted, it's taken me 10 years to go to complete phase 1. So phase 2, you know, one foot in front of the other. That's kind of the idea here. Baby steps, as Andy Edmond in Western Region used to say. So again, summarizing here, and again, we'll open this up. Again, significant threat to life and property is shown. The challenge with these, obviously, is there's overlap between other convective modes, tornadoes, giant hail, extreme damaging wind events, derechos. So polling, hey, this is going to be a wind-driven hail day, not so easy, but there are some commonalities to these, as Zach nicely illustrated. Radar signatures, again, seem to be our best evidence to identify these. And then, again, with the assumption that we still have that favorable environmental parameter space. But again, lots of work left to do to fully understand why and how some of these storms do that. And again, we continue to need a full database. And again, we keep asking for your help. So the slide here, the final picture that I'm going to show here, this was from an event that we had from a few years ago in the Des Moines area. This basically chewed up 5 to 6 foot tall corn to stubble. And in our social media Hall of Fame, this is still our winner. As you can see there, it's hard to see, but this had over I think it's over 3 million people now that were reached with this story. So not only is it interesting to us, but the public finds this interesting as well. So again, that is our Hall of Fame social media post, at least on in the Facebook world. So just a couple acknowledgements, and we'll open this up. Patrick Marsh and Andy Dean at SPC are instrumental getting us the data. Kelly at Aberdeen, who I worked with, she did a really nice job with the original coding on how to find these. So thank you to her. Daryl at IEM, as we know, Daryl's the man when it comes to a lot of this sort of stuff. Rod Donovan and Craig Kogel provided some really good context to a number of these events. Paul at Boulder's working with Zach on, again, a nice sounding board as well. And then again, as Zach mentioned, as well as Nick, we've worked on this project for a while. Again, we just need to push it to the finish line, at least in phase 1. So I think that's enough. I belabored this enough, folks. I will open this up to any questions anybody has. Zach and I are happy to entertain questions. Zach,
Yeah,
I guess first of all, is there anything I missed that you want to jump in there on?
No, I think we're good. Let's get to questions.
Yeah, great job, guys. That was a great tag team talk. Aaron, you're first in queue, so go ahead.
All right, can you guys hear me?
Yes, sir.
All right, well, great talk. Good stuff. Hail doesn't get enough attention, in my opinion. But anyway, just a few observations and kind of questions. First of all, one of the things we find even with like non-tornadic supercells, that's a clear signal for surging outflow and really strong winds, are these wet hail arc disruptions. And specifically, when you have these periods where the arc is disrupted and you see very high KDP, or in the absence of KDP, if the CC is low, you see exceedingly high, like 65, 70 plus DBZ. That's a wet hail signal. And that has all, as you go back to papers from 2008, such as Snook and Hugh, that talk about that being the source of a lot of the negative buoyancy and outflow. I was curious if you guys have looked at that, because we see that frequently in non-tornadic cases where you have a massive momentum surge that undercuts and kills off tornadogenesis, but also is the source of a lot of 70, 80 plus knot winds that, it's a supercell, so it's going to have hail. And the other comment I guess I had was, some of these cases, it's interesting how, if there is a tornado, a lot of times the hail is kind of hidden in the storm report database. I see that frequently. Matter of fact, I'm going back now and starting kind of a rough research project looking at only events where there was 2-inch or greater diameter hail occurring with population densities over like 500 per square mile. And what you find is there's a lot more concurrent events than what the storm data or climatological record shows. So that's kind of two questions or two different things there. But first, curious if you're looking at the wet hail issue, especially since that's associated with a lot of momentum surges and negative buoyancy. And then two, if you're accounting for any of these issues where you may have tornado events, but hail is not reported, even though realistically it does.
Zach, go for it. I'll let you go first.
Okay. So for the first part, the wet hail ZD arc disruption stuff, the answer is not formally. We haven't investigated that. The first kind of step was to get a database, and then the second part, once we kind of get this first part finished up, is to go ahead and start looking more into the why. So, we've noticed stuff like that at times. But it's not, formally in our database yet, but that's absolutely something we can look at. And then for the second part, you're probably right. We're looking just at what the ArcGIS query is giving us, so we're not necessarily looking at a lot of tornado events where there wouldn't be that corresponding hail and wind and storm data. But even just from looking at a few of the storms in our database, there's almost certainly times where hail is definitely being underreported, or you're just not getting the density of LSRs that you'd like. So, we mentioned at the start that we're probably undersampling quite a few wind-driven hail events, and I'm sure some of those are probably tornadic. I'm sure some of them are non-tornadic, but it's just one of the things we're going to have to live with for now until we get a better way, or a more efficient way of getting higher density hail and wind reports.
Yep, very good. Yeah, I just last comment here before I hand it off. I don't want to hog the entire time, but some of the concepts that you only have these wind-driven hail environments if the little shears week is a flawed concept, especially when you can do things like looking at the higher population density. All of a sudden, you see massively looped little photographs that can still have massive hail and especially wind-driven hail events. So anyway, very good, guys. Great talk.
Next
All right, thanks,
question is Phil.
Great talk, guys. More just a comment that may be helpful to you in the future. I just reviewed a paper. There are people down in Huntsville who are developing a database of hail damage based on satellite data going back to 2001. And so they're focused mostly from Kansas up to the Canadian border and from the mountains over to the Mississippi River. So that paper's still in review. But I think that like there's hundreds of cases. I'll just say that. So you may find that really useful as you start looking for cases that you can utilize for radar or environmental analysis or whatever. Hopefully that database will be available to you in the next couple months. So I just wanted to let you know that.
Great to know. Thanks, Phil. Appreciate it.
Go ahead, John.
Hey, again, I'll just add on. Great talk, guys. Really appreciate it, and especially appreciate the dual pole analysis that you throw in there. That's where my heart lies. But just more of a comment also. I saw that at the end of your part, Mike, the talk about the CM1 and things like that. Aaron and I have been working with some folks at NSSL, Matt Flournoy, and some others. They actually have people that can generate synthetic 88D images. So I kind of think that maybe for us to learn more with what we're seeing in the 88D, we may need to head that route to have some sort of collaboration with that kind of research, because there's only so much you can really prove with the 88D. On any given velocity slice, for example, you have a multitude of airstreams, so it's really hard to prove anything. But maybe if we could do, like you mentioned, trajectories and things like that off a synthetic or fabricated 88D image, they're doing some crazy things. So just a comment that maybe that's where we need to head with some of these ideas to at least prove things to help us in the warning decision-making realm.
I appreciate the comment, John, and absolutely. And that's kind of the goal. I mean, right now we don't have a great understanding. Like you said, there's a lot of holes in the observational data, and how and how do these form, and why do they form, and how do they evolve is somewhat of a mystery. I think we have some general ideas or theories, but you're right. I mean, this sounds like Holling's project part 2 here, potentially. So hopefully we'll get there. So appreciate the comment.